Okay, so today we're working on the rational root theorem. The idea behind this is that the rational root theorem is going to give us a list of possible roots that are either a whole number or a fraction. And now, does that mean that every one of the roots provided by this theorem is a root? No, not exactly. It's going to give a list of possible roots, because as of right now, if I'm not saying, well, let's divide this by something like n plus 1 or n plus 6, we can, so far in previous videos, we've shown how to prove if that is a root or if that is not a root. But what we haven't seen is where do we pick these roots up? Where do they come from? And they come from what we call the rational root theorem. Now, that's going to come from a ratio of the constant, my 8, divided by the leading coefficient as either a positive or a negative. So actually, this should the ratio of the factors of the constant divided by the factors of the leading coefficient. So the way we're going to show this is I'm going to list all possible factors of 8. So I know 1 and 8 or 2 and 4. So 1 and 8 make 8, 2 and 4 make 8. No other whole numbers will give me an 8. And that's my first one. And the leading coefficient is the number in front of my highest power of the variable, which in this case is a 1. So the only factors that I have right here are 1. And so I'm going to take a ratio of every possible combination of these. I'm going to take each of these over a 1. So my list right now is 1, 2, 4, and 8. And I'm actually going to list this as both a positive and a negative. Cool. And so if a root exists, it's going to be one of these 8 numbers. Does that mean this polynomial has 8 roots? No, it has 3 roots at max. So that means that at least 5 of these are not going to work. More of them may not work if the roots are irrational, in which case all of these will not work. So we remember the fact that to test each one of these, we can simply use synthetic division. So let's go ahead and let's test out. I like to test out the ones here in the beginning, because most of the times if we notice that we have coefficients right here, or if we have big numbers in there, these, I guess you'd call them extreme roots, don't tend to last, and we'll see why here in a second. So let's go ahead and start in the middle, like either at a 1 or a negative 1. So let's try out a root of 1. And we're going to set up synthetic division, or I guess you would say synthetic substitution, and say, okay, if I plugged in a 1, 1, negative 5, 2, and 8. And I'm going to plug this in and see what we get. So I'm going to drag down my 1. 1 times 1 is 1. Take the difference, or I guess you'd say the sum is going to give me a negative 4. The product is negative 4. The sum is negative 2. The product is negative 2. That gives me an answer of 6. Okay? So basically what's going on is, as this graph is moving, we know this graph is going up and down and up. It's doing something like that. Well, when I plug in the value of 1, so let's see, 1 right here, I guess I should have dipped that a little lower, but we know that the graph is still up a little high. It's actually up at the value of 6. So I know that if it is sloped like this, a number to the right of 1 means it's going to dip down, or let's say it dips this way. I know the number to the left one. So I need to figure out which way is this decreasing. So the next one that I plug in, it's either going to be lower or higher. It's going to tell me which direction to go. So first off, we know that negative 1 substantially, or not negative 1, positive 1 is substantially not a root. That will never pop up again, because if it's not a root of the parent, it won't be a root of the factors later on. But let's try a different number. Let's try 2. And let's see if we get closer to 0. Are we going to get closer to 0, or are we moving farther away from it? So 1, negative 5, 2, 8. Let's see what we get. Product, sum, product, sum, product, sum. Boom. So when I plugged in a 2 as a move to the right, it actually went down and it hit the axis. Exactly. So I know that one of my factors, or one of my roots, is at positive 2. So I'm actually going to pull that out and see what my new equation looks like. So if I pull out a 2, we know that, let's see, if n is equal to 2, if I were to solve that for 0, that means I subtract 2, so n minus 2 is equal to 0. So there's the factor that I'm pulling out. So n minus 2. What's left is going to be n squared is going to be an n squared minus 3n minus 4. So I found one of the roots. I have 2 left. And now this can either be solved via quadratic, of which we'll be able to look at and say, hey, I can substantially say that n minus 2, what factors of 4 make a difference of 3? Well, that would be n minus 4 and n plus 1. But in case we didn't know this, just by factoring a quadratic, we would create a list of possible numbers, just like what we did right here, using the 4 and the leading coefficient of 1. Let's see, numbers that make 4. So 1 and 4, and then 2 and 2. Numbers that make 1 are 1. So my list right here would be 1, 2, and 4. Positive and negative. Okay. We already know that positive 1 won't work. So our list right here, we can get rid of that positive 1 because we've already removed it. We also noticed that the 8 and the negative 8 are not in our list, which means that we could technically go back and remove these from the start and say, hey, we didn't even need to start trying these, but we didn't know that at the time. This is a smaller list, so we're going to use the smaller of the 2 lists, because remember, it's possible roots. These aren't telling us all the roots. It's telling us out of all the numbers it could be, it's going to be one of these 8. Well, now we're down to one of these 5. We know by factoring the quadratic, it's going to be positive 4 and negative 1. But assuming that we don't know that yet, and we just working off this list, let's try one. So let's actually try the 4. Let's plug in a 4. And remember, I'm plugging in a positive 4 because if I set that equal to 0 and solve it, my n equals a positive 4. So 1, negative 3, negative 4. Again, I'm using the coefficients right here. Drag down my 1, take the product, take the sum. Take the product, take the sum. Perfect. So I know that 4 is a root. And basically what we could do is we could do the same thing that we did right here and say, okay, well in that case, if n equals 4, subtract it, n minus 4 is equal to 0, there's my factor, and we could factor it out of here, and I could say, okay, I had my n minus 2, I pulled out an n minus 4, what's left? Well, that's an n, that's a positive 1, so I'd have an n plus 1, which is exactly what we got right there. And there we go. We have our factored form of this polynomial. And so we see that the process itself isn't too bad. It's just kind of rinse and repeat. Make a list, try out the numbers until you hit a 0. If you don't, scratch it off. Once you hit a 0, pull that factor out, write what's left, and restart the process. If the list is smaller, use the smaller list. If the list is bigger, use the smaller list. Always use the smaller list. So let's try something very similar to that, except for this time we have a leading coefficient. So we're finding factors of 5 over factors of 4. So my factors of 5 are going to be 1 and 5, just 2. My factors of 4 are going to be 1 and 4, or 2 and 2. So unfortunately, we have a little bit of a list going on here. I'm going to take both of these over 1, which in case 1 over 1 is just 1. So positive 1, negative 1. I have positive 5, negative 5. But I also have to include these as the denominator as well, which means I have a positive 1/4 and a negative 1/4. I have a positive 5/4 and a negative 5/4. I have a positive 1/2 and 5/2. 5. Now, this is a really horrible way to make a list, but we know that it's going to be one of these numbers. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible options. Again, now we realize that it could be one of these fractions, but using synthetic division like we did earlier, let's start with the whole numbers. Let's cross our fingers and hope it's one of the whole numbers. So again, I like to start right in the middle. I'm going to pick a number like 1. So let's try the number positive 1. 4, 3, negative 6, negative 5, and let's see what we get. Product, sum, product, sum, product, sum. Oh, nope, that didn't work. So we know that as we're graphing this thing, we know that at the value of, let's draw. At the value of positive 1, our graph is still way down here at negative 4. I don't know if it's going up or I don't know if it's going down. So one of the ways that I could do is I could skip over to 5, and let's see what happened there. Let's try the next number. Well, first off, 1 does not work. I can cross that off my list. Let's try the number of 5. Plug that in. Product, sum, product, sum, product. I can already tell that this is careening off. Do you notice how it's getting bigger and bigger? So that's showing us that it is moving towards an infinity of one sort. So we just need to really check on the sign. That's going to be a positive 545, and that's going to be a positive 540. So unfortunately, what I know that by the time I hit 2, 3, 4, and 5, by the time I hit 5, my graph has moved from negative 4 all the way to 540. I don't know what it's done in between here, but guess what? I know between the numbers 1 and 5, I'm going to have a 0. Because if it crosses like this and goes up, if it just kind of goes straight there and just wiggles a little bit, I'm still going to cross. If it crosses way up, way down, and goes way up, I'm going to have to cross this line, which means a 0 is somewhere between 1 and 5. So I'm going to have to find some numbers that are between 1 and 5. Now, it may be irrational, but I know I have a good choice of numbers between 1 and 5. That's too small, so it's either going to be 5/4 or 5/2. I'm going to deal with 5/2 first. Hold on. Let's get rid of that positive 5, because that doesn't work. So I'm going to start with 5/2. If 5/2 doesn't work, I'm going to go to 5/4. If neither one of these work, that just means it's an irrational root. But regardless, let's try our first number that's between 1 and 5. So 5/2. 4, 3, negative 6, negative 5. Let's work this out. 4. Okay, so 4 divided by 2 is 2. 2 times 5 is 10. It's going to give us a 13. Oh, joy. This doesn't look like it's going to work out nicely at all. So 13 is going to give us, let's see, 5 times 10 is going to give us 50, and 15 is going to give us 65 halves. If I add this up, that's going to be negative 12 halves, which is going to be 55, 53 halves, 53 halves. Again, I multiply this. So that's going to give me something over 4. 5 times 53, that's going to give us 5 times 50 is 250, and 15, 265. And we see this is just careening off. We know this is not going to be a 0, but I kind of want to see if it's positive or negative to know between what two numbers we get. Okay, so divide that by 4, that's negative 20. So that is going to be negative 20/4. So 265 minus 20 is 245 over 4. Still a really big number, which means that we're still way up here somewhere. So something's either creeping down, or maybe we've gone down and we're going back up. We're not exactly sure. But I know that 5 halves did not work. And so this is one of those, it's kind of a last ditch scenario. We've tried 1, 2, 3, and we're on our 4th number. That happens, but we just keep plugging. We know we've got it max 1, 2, 3, 4, 5, 6, 7, 8, 9 tries left, and if it's not in here, it's not in here. It's not infinitely many, we just have to keep trying numbers. So let's try our other number that's between 1 and 5, 5/4. Plug these in. 4 over 4 is 1, 5. That gives me a sum of 8. 8 over 4 gives me 2 times 5 is 10. 4. 4 over 4 gives me 1 times 5 is 5. Bingo, we found it. So what I know is I pulled out a 0 of 5/4, which means if n is equal to 5/4, multiply by 4, 4n equals 5, subtract the 5, 4n minus 5 is equal to 0. There's my factor. Now we notice that we tried a fraction, but our factor actually has a 4 in there. So I'm going to go ahead and divide all these by 4. So it's going to be a 1, a 2, and a 1. That's actually what we're dealing with, because those all had to be divided by my coefficient of 4. So 4n minus 5. I'm dealing with, let's see, n squared plus 2n plus 1. And now at this point, it's actually cha-ching, that worked. At this point, we could use this and keep going through these, but remember, we can make another list and make it a smaller list. We could try, okay, all possible factors of 1 over all possible factors of 1. Guess what? I'm trying a positive 1 or a negative 1. Well, I already tried positive 1. I know that doesn't work. Negative 1's the only thing left, because my list right here, remember, it's 1 over 1. I have a positive 1 or a negative 1. We have already proved that positive 1 doesn't work. So my only possible factor, or my only possible route to try, is going to be that negative 1. So I'm actually going to bleed into this next cell right here. Say 4n minus 5, n squared plus 2n plus 1. I'm going to try out the negative 1. Come to think of it, we probably should have tried the whole numbers first, but we noticed it was between these two, so it is what it is. Let's work this out. Carry it, so take the product, take the sum, take the product. Hey, guess what? My other factor is a negative 1. And so if I say, okay, n equals negative 1, and plus 1 is equal to 0, there's my factor. So I have my 4n minus 5. I have my new n plus 1. And I have my new n plus 1. Ooh. So there we go. Alternatively, what we could have done is we could have factored this and say what factors of 1 add up to 2, and we would have gotten a 4n minus 5. Well, what factors of 1 add up to 2? Well, 1 and 1 add up to 2, and we could have done it that way, but synthetic division got us there. And there we go. Okay, so today what we're working on is working on the rational root theorem. Now, the rational root theorem, we're working on an extension called the intermediate root theorem, which states that if you plug in a number a and b into the function and you get opposite signs, then a root exists between a and b. Now, typically this is taught at a higher level, but because we just went over synthetic division and where the roots are located, I figured this would be a very good extension right now to kind of expose you to where you end up finding the roots. And so let's take a look. If we try out f of a, which means we're plugging a in, we use synthetic division to test that out. So -4, I'm going to try 1, 10, 31, 30. And I'm going to see what happens when I plug in the -4. So 1, I multiply, -4, and then I add 6. Multiply and add. Multiply and add. So I have a positive 2. Now, if when I plug in b and I get something other than a positive, I know a root exists between these two numbers. If I get another positive, it doesn't really tell me anything. There could be no roots, there could be 2 roots. We're not really sure what it tells. So let's go ahead and plug in the -6 and see what we get. Okay, so draw our line. This time, multiply, combine, multiply, combine, multiply, combine. So -12. Huh. So I know between a positive and a negative, a root must exist because the only way the graph can go from positive to negative is by going through the axis. So what we're seeing right here is we're seeing, so at -1, 2, 3, 4, 5, and 6, the graph went from at -4, it was at 2, it was somewhere up here, and then at -6, it somehow got down here. And the only way I can get from one point to the other is by crossing the axis, which means a root has to exist somewhere between -4 and -6. Not necessarily exactly right here, because it could be bending or shaping, but we know somewhere between -4 and -6 a root exists. So perfect. So yes, a root exists. Boom. Let's try that again. So now this is a slightly longer one, but the idea is the same. I'm testing 2 values and I want to see, does a root exist between these 2 numbers? So I'm going to test out -4, 1, 12, 47, 72, and 36. And then I'm going to test out 0, 1, 12, 47, 72, 36. And so I want you to go ahead and pause the video, try it on your own, and unpause it when you're done to see how well you did. Okay, so let's try it out. So carry my 1, I multiply and combine, multiply and combine, multiply and combine, multiply and combine. So I've got a negative value right here. So if this is another negative, doesn't tell me anything, doesn't tell me anything useful at least, but if I get a positive, it does. So let's try it out. Multiply, combine. Zeros are easy because you're literally just copying down the next line, because every time you multiply 0 times this, you get a 0. So I know that every multiplication I get a 0, because 0 times 12 is 0. I add, 0, add, 0, add. Ooh. So I have a positive and a negative. So that's perfect because I know on the graph, if I went from 0 to -1, 2, 3, and 4, at -4, I was at -12 down here. And by the time I got to 0, I'm way up here at 36. And the only way, no matter how I move, is I have to go through the x-axis, which means a 0 does exist. So yes, a root does exist. So now what I want you to do is I want you to try this one. Tell me whether or not a root exists between -6 and -9, and tell me what you notice. Okay, assuming that you've moved forward with this, we're going to try out a -6 and a -9, 2, 30, 118, 90, 2, 30, 118, and 90. Let's check. So for the first one, -12, 18. Let's see, that's going to be 60, and that's going to be 48. That's going to be 108, which is 10, and -60. So I get a positive 30. For my 9, let's see, that's 18, 12, that's 90 and 18, which makes, I'm gonna wait again, 10 and negative 90. Okay, so what you got right here is you noticed you had a positive and a 0. Now tell me, does a root exist between -6 and -9? Well, the answer is no, because that did not go from a negative to a positive. But we noticed that the -9 is a root, because when we got our answer, we got a 0. So we know that on the graph between -1, 2, 3, 4, 5, 6, and 1, 7, 8, 9. So between -6 and -9, at -6, we were at 30, somewhere way up here, and by the time we got to -9, we were on the axis. So we're not trying to find between here, does a root exist? We know a root exists on the -9. So no, a root exists at, let's see, this is x, so x equals -9. Root doesn't exist between them because it exists right there. Okay? And for the last one, let's try this one out. So I'm trying out -2 and -3. So 3, 16, 23, and 6. Go ahead and tell me what you find. Okay, let's see how well we did. -6, 10, -20, 3, -6. Oop, looks like it's gonna be the same thing. I'm not gonna find a root between there because I found a root at -2. But just to go ahead and play around with the next one, we're gonna see 3, -9, so that makes it 7, 21. Oop, I don't know what I just did there. That makes it 2. Oh, lo and behold, they're both 0. So according to this definition, I didn't go from positive to negative, so this should say that it's nothing special. We can't tell, so we're going to say no, because both, let's see, we're still at x, so x equals -2 and x equals -3 are roots. And now the reason why we include this here is because if -2 and -3 are roots, if I try -1 and -4, I know I have 2 roots between those, right? But what happens when I plug in the -1 and the -4? Well, let's try it out. So 3, 16, 23, and 6. When I plug in numbers around 2 roots instead of around 1 root like we were doing earlier, what does the answer look like? So 13, -13, 10, -10, -4. So I got a negative, 4, that's a 7, -22. So I get a negative and a negative. Now, we talked earlier about why this isn't anything special. It doesn't mean that there's no root, because we know not only is there a root, there's 2 roots. So why did we get 2 negatives when we know, in fact, there's not only 1, but there's 2? Well, let's take a look at what the graph is doing. So from -2 to -3, we have a graph. Let's give ourselves some space right here. Let's actually use the bottom of this. So between -2 and -3, we know we have a root right here at -2, and we know we have a root right here at -3. Which means that, okay, so if at -1, the graph is at -4, let's just assume right there, and at -4, the graph is way down here at -22, it looks like what the graph is doing is it's going from here to here and like that. So we know that between our 2 values tested, there's a maximum point. But if we were to test a wider variety, it would look like the graph could be just going straight from here to here and never crossing. Little did we know it crossed twice. So again, if you get the same signs, it's not an indicator that there is no root. It's just an indicator that the graph hasn't actually crossed the axis between those two values. Could have crossed twice, could have crossed 4 times, could have crossed 6 times, 8 times. We notice that if it crosses once, that's what we're looking for. And that's the point of today.